And now I move on to the first topic of my presentation on the probabilistic prognosis of wind generations. So we, traditionally, it has been, we have to say that the forecasting of wind energy or other renewable is not new, a research topic. It has been, there has been a quite intensive research in the past. And if we can classify the forecasting of wind energy, forecasting of wind powers according to the time horizon. Generally, we can consider there are very short-term, mid-term, long-term forecast. Very short-term, the range is up to a few seconds to 30 minutes ahead. Or short-term is actually 30 minutes to 48 hours. Mid-term can be up to 1 week. A long-term, 1 week to a year. The long-term, as you know, is mostly for planning purpose. Short-term is mostly for the dispatching, economy load dispatching, unique commitment, those kind of purpose. And regarding the methodology applied for the wind forecasting, there are physical methods based on the numerical weather prediction models. There are also statistics methods based on vast amount of data using the different statistic models. For example, the AMA model, average, auto-regression moving average model, or artificial neural network models. For example, the SVM or ERM, extreme learning machine. Nowadays, deep learning model, deep learning neural network is very popular. For example, the CNN network model, very popular. Also, there are hybrid methods combining the physical methods, physical models, alongside statistical methods. Then the challenge in facing the wind power forecasting that we know in a lot of countries, including particularly since I used to work in Denmark, so we know that Denmark is really the champion in the world in terms of the wind power penetrations. I remember it was by 2008 in Denmark, the wind penetration already reached at the 25%. Nowadays, I think in Danish power system, the penetration of wind already above 30%. So because the wind is very fluctuating, because the wind is really it's not controllable, it's really depending on the weather systems. So the high penetration of wind power brings troubles for the balancing control in power systems. If you look at the figure here, this figure is taken from a wind farm in South Australia. So you can see that this is only for 2,000 hour period, and that's around a month, around that. Several, more than half year. So you look at it, very chaotic. Sometimes it goes to near zero, sometimes goes to very high. So these fluctuations actually creates troubles for balancing control in the power system, because we know that in the power system operation, the most important priority for the power system operator is to keep the balance between the supply and demand. So if we have such fluctuating generators injecting power into the grid, we have to accordingly have some other resources matching with this such fluctuating amounts power. So in the past, most research has been focusing on the so-called point forecasting of wind power. That means we just predict into the future, either by one or several time step ahead, what is the exact amount of the wind power generations. This is so-called point forecasting. You give one single values into the future, either one or two or several time step ahead. However, we understand that there is a non-stationarities due to the chaotic nature of the weather. What is so-called stationarity? That means actually, in terms of the statistic, the mean values, the variance of the time series of the wind generation is always changing. That's so-called the non-stationarity. So according to the traditional those statistics series, this kind of non-stationary time series is very difficult to build up an exact statistics model for the forecasting purpose. The prediction errors are kind of unavoidable, and most importantly, very significant sometimes for those traditional point forecasting methods. This is really observations. If you try those traditional forecasting methods, you will find out sometimes those models can give you reliable prediction, but sometimes it can give you very wrong, very inaccurate results. So it's really the traditional those statistics methods can never give you a consistent performance for the wind power forecasting. This actually inspires the research scholars from around the world to think of new principles, new philosophies in conducting the forecasting of the wind powers. Actually, I have to say that this not only applies to the wind power, but also apply to any other renewable energy, such as solar energies, which is kind of dependent on the weather systems. So as I said, that because of these unavoidable and very significant errors involved in the traditional forecasting methods, so the researchers have come up with the idea that why not we introduce the so-called probabilistic forecasting to predict instead of an exact value into the future. Why not we just quantify, we give a quantification of the possible uncertainties, the possible errors involved in the forecasting into the futures by constructing prediction intervals associated with the confidence level. So that's the core idea of why we go for the probabilistic forecasting. It's mostly because the inadequacy of traditional point forecasting in dealing with the renewable energies, dealing with the particular wind. So the figure here, the figure below, is actually give you a concrete comparisons between point forecasting, probabilistic forecasting. Now, in the point forecasting, if we see that the red curve is giving you the actual value, the blue curve is actually giving the forecasted value. For example, I think this example is one step forward forecasting. So you can see, okay, there's always difference between the forecasted and the actual values if we plotted them into one pictures. But if you go for the probabilistic forecasting, rather than we giving one specific dots for the blue curve, we are giving you a range represented by these green colors. to encapsulate this red curve. Red curve is the actual values. So then, of course, besides this interval, actually, those intervals also associated with confidence level. That means how confident the actual values can fall into this interval. That's the core idea of the forecasting, probabilistic forecasting. Then, what's the prediction intervals? It's not the mysterious. It's actually you can understand that the prediction interval actually is to quantify the uncertainties between the merit values, in other words, the target, and the prediction value by your models. And that means that we actually, in doing the probabilistic forecasting, we are trying to constructing this conditional probability relationship between your model output and the actual values. You can also understand is to constructing the conditional probability relationship between your model input, forecasting model input, and the targets. Okay, so now let me give a little bit review on the traditional probabilistic forecasting methods to construct the predictional intervals. Before our research, before our paper published in 2014, actually today's presentation is mostly based on our work in the 2014. Before that paper was published, most existing methods for probabilistic forecasting are based on either the so-called quantile regression or the so-called output conditional prediction interval methods, or the weather ensemble prediction methods, or the kernel density methods. These methods are mostly relying on the quantile analysis of the point forecasting errors, with or without the some assumptions, prior assumptions. For example, they assuming mostly in those methods, they are assuming the errors of forecast of the point forecasting results are kind of Gaussian distribution. That's a common assumption involved in those traditional methods for constructing prediction intervals. Therefore, those traditional methods usually involve several steps to calculate the prediction intervals. Firstly, they will prepare the training data set, then constructing a point forecasting model, then compute the forecasting errors, then estimate the prediction intervals construction model, then test the resulted prediction intervals. So these steps are commonly involved in those traditional methods from A to D. Regression, kernel density, they all involve those steps as the traditional methods. Then in our methods, later on I will show you the detailed steps, but the core of our methods is to apply the so-called extreme learning machine. If you guys know that this ELM was invented by our friend Professor Guangbing Huang with the Nanyang Technological University in Singapore. This algorithm is one of the, I would say, one of the new advances in the single hidden layer feed-forward neural network. So the advantage of this extreme learning machine is that the training of such neural network becomes very simple. So it's a single hidden layer network. Then in the training process of this ELM, only the output weights need to be analytically determined. There is no, if you guys are familiar with the traditional deep network, you will know there are always so-called the iteration procedures to update your the weighting factors in different layers. But for this ELM, because of a very special design, so the calculation, the updating of the weighting factors become very simple. It's just one step. Matrix calculations already can calculate the weighting factors directly. So this is the most important reasons why we also apply this ELM in our forecasting models. Of course, there's other reasons. For example, the ELM also proved to have very good regression capability. That's also another very important reason why we apply this ELM in our methods. If you want to know more details of this ELM, there's a lot of literature written by either Professor Huang or other scholars. Search and read for details. So the ELM, there's no iterative gradient-based training speed become extremely fast. And also it has superior generalization and regression capability. That motivates us to apply the ELM. How do we apply them? We actually use the ELM to create, to generate, to forecast, or in other words, forecast the so-called prediction intervals in our methods. Now, how do we create or construct our prediction intervals? We actually construct it using the directly by applying the so-called prediction interval evaluation indexes. First, the index we are applying for the PEI construction is the reliability index. And also we apply another index of sharpness. Of course, reliability, as the name tells, you can understand, reliability is to assure that the actual value can fall into your created or your constructed prediction intervals. This requires your forecasting models to be reliable in terms of the accuracy. What is the sharpness? Sharpness actually is besides requiring your actual values fall into the prediction interval, we also want to make sure the prediction intervals can be as narrow as possible. That's why we have this name, so-called sharpness. So for the reliability, the specific index for evaluation is so-called ACE error, average error, coverage errors, equals to PICP minus the PINC. PICP is the prediction interval coverage probability. PINC is the so-called nominal confidence. What is a PINC? So if, for example, if we are constructing a prediction interval with a 90% confidence, then the PINC should be 90 confidence. That's the so-called nominal. Then how do we calculate the PICP? Just by applying this equation. While the CI either equal to 1 or equal to 0. 1 stands for, okay, the actual results fall into the prediction. Then CI equals to 1. If for all of the intervals, the actual value for all of the intervals, it will give a 0. So then ACE actually can well evaluate how reliable the actual values will be covered by the prediction. For the sharpness, to evaluate sharpness, interval score is used. Interval score is defined by this equation to consider if the actual value is less than lower bound. L stands for lower bound. U stands for the upper bound. It's PI, prediction consisting of lower bound and upper bound. So this interval score is calculated according to the equation. So I won't go through the details, but if you're interested, then you can go to our paper. It's not difficult. It's really, you just read it. It's quite easy to understand. So based on this, this two index. Actually, in our methods, very simple. We using the ELM, extreme learning machine, to formulate this upper bound and lower bound of the prediction intervals according to certain confidence levels. Then calculate the ACE, formulate the ACE and the interval score. Then eventually we form the cost functions for the optimizations. The cost function very simple. It's just ACE plus we use a sum weighted optimization formulation. This is the formulation we used in our first paper published in 2013. I remember in the section on power system. That's the very initial version of our formulations. So now, because the cost function becomes such a simple optimization functions, so this actually shows that our method have been able to kind of simplify those multiple steps involved in the traditional probabilistic forecasting method into only one optimization steps. And this optimization functions actually can be solved by any solved by the heuristic methods for simplicity. For example, the particle swarm optimization, PSO, or any other heuristic methods. Later on, actually, in our later papers, we have been able to linearize the optimization, these optimization functions, and apply those classical linear optimization methods to solve the equations. So then we accordingly we just implement the methods by solving the models using the PSO, and you can see in this flow chart of our algorithms, we just use the PSO very quick. In our experiments, so we have been trying out the methods for case studies, and then because the optimization objective function is very simple, so the solving procedure very quick and take quite short time to finish. Here we are showing you some results by using some of the data from wind farm in Australia, and then we make a comparisons to other methods. For example, the uniform methodology persistent method. Our method involved our paper in the 2016. We gave a name as a DF, direct interval forecasting methods. So our method outperform other methods in terms of both ACE and PICP, as well as the interval score. This is sharpness. So here we are showing you some of the results. Showing you the red curve is the actual value. The blue and the green one is the upper and lower bound. So this is the results with 19% confidence. So short summary regarding our research in this direction. So we have basically propose a new framework for the so-called direct interval forecasting methods for wind power based on the extreme learning machine and PSO. And there's a novel optimization objective constructed, including both reliability and sharpness. With high flexibility, this method provides a general framework of probabilistic forecasting for not only wind power, but also other renewables such as solar. There's high potential in practical applications because the efficiency of the algorithm is very high. So here I'm also listing quite a few papers we published in these areas, particularly the presentation of the methods we just present to you is based on these two papers published in the 2013 and 2014. So in this area, we actually have two invited papers from different journals. We also have two highly cited papers according to the ICI. We are applying for several patents. So okay, this is the first research I'd like to share with you. Then next is again also about wind power. So the next topic is the so-called LVRT, low voltage right-through control, or the defect wind turbine system. We understand this is a low voltage right-through control is one of the most important requirements for grid integration of wind energies. So we have been doing a lot of work in this direction as well. And then from the name, you might be curious what's the so-called LVRT. It stands for, as I said, low voltage right-through. So then first question, where is the low voltage? Low voltage here is mostly referring to that at the terminal bus. The defect, the wind generators see a low voltage. Mostly referring, or either you call it point of common coupling, or you can call it just terminal bus of the wind turbines, of the wind generator systems, having a low voltage. Then why we so care about this? Simply because if you have a low voltage at the PCC point, then mostly the wind turbine system will experience overcurrent either in the rotor circuit or the stator circuit. You will also possibly experience over voltage in the DC link, overpower in the inverter as well. So this circuit is showing you a schematic of defect system. So we have a turbine connecting through maybe some gearbox and connecting with the generators. Then defect, you have a rotor circuit, you have a generator, you have a stator circuit. Stator circuit is going, and rotor circuit is going through a rotor side inverter, back-to-back inverter, and then the grid side inverter. Then together with stator side, it will go connected with the outside grid normally through a 3-winding transformer. Here actually we have been omit that. There should be a 3-winding transformer. Then the other question is why we have the low voltage in the PCC. This is the root cause of having this low voltage, mostly because there will be faults. Very commonly, there can be faults happening from time to time in the power systems. For example, single phase, face-to-face, etc., etc. Those faults are very common. We know that. For example, for the large system like Indian power grids or the mainland China power grids, every day, I think there can be up to quite a number of faults happening. And thanks to the protection, the relay systems, normally once we have a fault, and those faults will just endure for a very short intervals and then cut off by the relay systems, circuit breakers. So that's why it's very common to having the low voltage carrying the power systems. Now, what bother with that? What's the problems with that? Simply, if you have such a short voltage, because you have overcurrent, over voltage in the wind turbine systems, and the protection system inside the wind turbines normally will automatically trip off our wind turbines. This is for self-protection purpose. Once we detect there's overcurrent or over voltage in our defect system, definitely the protection system, for example, the protection for the grid side or the rotor side converter will immediately turn off the inverter, then turn off the whole systems for sure. That's for the self-protection purpose. This is understandable. But the problem is that in the past, if the wind penetration level is low, then once you have a low voltage event, then the wind turbines trip off. It's kind of tolerable because you have less contribution of the power to the system. But once you have a high penetration of wind power, for example, if you have up to 30% of wind penetration, then there is if there is a low voltage happening in the systems, then all of your wind turbine trip off. This will create a significant shortage of power contributions to the grid. This will create, accordingly, the imbalance problems in the systems. So this is the main problems why preferably we actually not like that the defect would trip off directly during any shock events. Instead, according to the grid integration requirements, we want to make sure that for some of the low voltage events, which is less serious, less severe, we may require the wind turbines to remain online so that they can rest through the faults, then helping to keep the supply and demand balance of the power grids throughout the whole procedures. So then this actually becomes a kind of grid integration requirements for the wind turbines, for the wind generators. So in a lot of those leading countries, advanced countries for the renewable energy, like Denmark, Spain, they are I would say they are the leading countries who introduced these requirements. And currently the curve, the profile here I'm showing you is actually the so-called LVRT requirement directly taken from the Danish grid integration code for the wind energies. So what we can understand, what we can get from this curve. Firstly, of course, the x-coordinate for this curve is time in the units of milliseconds, while the x-coordinate of this curve is actually the terminal voltage in terms of the percentage. So what the curve tells, they actually tells that if your wind turbine is seeing there is a grid fault causing the low voltage at the terminal voltage, the terminal bus or the PCC point. If such low voltage falls into the grid area here, then your wind turbine must be able to survive through the whole event. Alternatively, if we have a low voltage event that causing the terminal voltage profiles goes out of these gray areas, then your wind turbines will be allowed to trip off for this event. So this is basically so-called LVRT requirement according to Danish power grid code. You can see that this requirement is quite strict, quite high, because as you can see, starting from 0, that means once there's a lower voltage occur, so this will require this profile actually goes down directly to 0 voltage for 150 milliseconds. So this actually represents the most severe case where you might have faults directly happening at the terminal bus of your turbine, causing 0 voltage. So this profile, this requirement sometimes with a 0 voltage. We also call it ZVRT requirement. In some of literature, we call it ZVRT because it is more challenging to implement. but anyway, this is this represent perhaps the most strict requirement for LVRT. So in the past, a lot of research work has been done for developing different kinds of methods for the LVRT. In the early days, there's some methods. There's some methods actually. Some engineer propose that to let the wind turbine contribute to the power systems during the fall. What we can do is we can, once there's a fault, we just disconnect the turbines, then reconnect back shortly afterwards the fault, once the fault is cleared. But however, the main problem is that during the fault, the defect is not really online. And also, once you're doing this, you will understand this actually involves switching operation of the high voltage circuits. It's definitely not preferable. Then the most popular method is crowbar solutions. Nowadays, the crowbar is still one of the so-called industrial standards for solving the LVRT. So what's a crowbar? Crowbar is actually a circuit, three-phase resistor circuit to short circuit the defect rotor during the fault. So that's why I make a note here that this actually involve additional hardware system, three-phase short circuit resistors, and to kick in. Once there's a fault detected, it will kick in to short circuit the rotor circuit of the defect to dissipate the extra energy generated by the wind turbines. But you have to understand, once we have short circuit the rotor circuit of the defect, and then the defect actually turns from a generator into a induction machine. And that means you are changing from a supplier to a consumer during the fault. And we know that induction generator actually, induction motors, induction machines actually consume a lot of reactive power. So during the low voltage, already the system is suffering from less reactive power. But by applying the crowbar, you actually exacerbate the conditions by absorbing more reactive power. This is not preferable. So that's those are the major shortcomings of the crowbar, even though the crowbar solution has been quite successful. Then there's also some interesting methods, for example, the demagnetizing methods. In some of the paper, I remember this one paper published in the triple E transition on the energy conversion. It's very interesting. They consider that the faults is caused by the different, sequence of the currents. Overcurrent during the LVRT is caused by different sequence current. They do the decompositions of the original current, then accordingly apply the control circuit to compensate those different sequence current. But however, this method is very good in theory, but the problem is that it involves complicated control circuits, and accordingly it involves some time delays. Because we should understand that for the LVRT, we are dealing with the events in the millisecond scales, so we really require that your control method must be quick enough. So in summary, that the most existing method can have loss of a P and Q control because they were kicking some additional hardware, and they also careless about providing the reactive power support to the grid during the fall. That's the major shortcoming of those existing methods. Then accordingly, in this direction, we have since I was in Denmark, we actually collaborating with many other colleagues to work on some interesting solutions for the LVRT methods. So we have actually published quite a number of scientific papers, and we're involved in one SCI highly cited paper, also one patent granted. The basic idea of our method is that we try to look at the problems from energy perspective. So firstly, we understand why we have this overcurrent or over voltage defect circuits during the low voltage faults. It's simply because there is continuous energy injection into the induction generator during the fault. Because when we have a low voltage fault, it doesn't mean the wind stop blowing. Wind is still ongoing. So there's still continuous power input from the wind to the generator. So that generator is continuously generating the electricity, generating additional energy. But at the same time, terminal bus having a low voltage, this is create actually a bottleneck for the effects to output the extra energies. That's why we have the over voltage or over current in the systems. Then accordingly, we see that the critical problem now is actually how can we deal with this extra energy. In the traditional core bus solution, what they do is they introduce the short circuit circuits with a resistor for energy dissipations. Instead of doing that, in our method, we actually revise actually the control circuits for the defects, so that we can allow that the jet rotors of the defect to accelerate during the fall, such that those extra energy can be well stored into the kinetic energy of the rotors temporarily during the LVRT. And this can well solve the extra energy problems during the LVRT. Later on, once the fault is cleared, we also can recover the control to the original one. Then allow the generators, induction generators, to send back the extra energy in the rotor to the grid. So that's the basic ideas in our methods. So nonetheless, when we implementing this method, we have to understand that for any low voltage events, there's different stage involved. For example, when you have a low voltage, you are events. You will have the first stage when it's falling, then stabilizing. When it drops to the valley, it is getting stabilized. Later on, once the fault is recovered, and then the voltage will also recover. So basically, a typical low voltage fault in the power grids will have these three stages. Accordingly, when we designing the new control strategy for read-through, we have to consider this stage. Then the control method, we initially, because we actually published several papers in this area. So initially, when we try to implementing our idea of accelerating the rotors, what we do is that in our very first paper, we try to set the control signals for the electrical torque to 0 for the defect, which means that we try to make the electrical power output from the defect generators to be 0. And so this is very easy to implement. We just need to set the T equal to 0. Accordingly, on this here, the control loop showing here is the control loop for the rotor side converter. So what we do is just replacing the original control according to the MPPT, the maximum power point tracking, means setting the reference rotation speed for generator. We're replacing that by a 0 signals input. Then this actually has proved to be very effective, at least according to our simulations. Then later on, actually, we have improved the methods in our second paper, because we realized that not necessary that in all the low voltage events, the faults will cause voltage drop to 0. So accordingly, in most of the fault events, we just have a low voltage events. We still, during the fault, we still can have some of the voltage, definitely less than the rated voltage, but maybe much above the 0 voltage. So to consider that, so rather than setting the TE, the electrical torque for the generator to be 0, we just proportionally set the control signals according to the low voltage during the fault. So as this equation tells that we actually set the control reference proportional to the actual voltage during the fault. Now, of course, we are applying a small factor here, tau, and this tau is a kind of security margin, as you can understand. We're trying to also make sure that the control signal is not above, go above the actual low voltage. So we set the tau smaller than 1, normally it's 0.5, to make sure the control scheme is secure enough to avoid any possible overcurrent, over voltage systems. So accordingly, in our second paper, we have revised the active power control circuits to be like this. Figure here. Then besides that, we also revise a little bit about the grid side control to ensure there's no over voltage in the systems. And in addition, nowadays, for the grid integration codes, the requirements for the wind generator becomes more and more stringent in terms of the controllability. So besides the active power aspect, we understand the LVRT I just present is really regarding the active power control aspects of the wind generators during the fault. So nowadays, the leading countries like Denmark and Spain, they actually moves from not only the active power, but also the reactive power control aspects during the LVRT. So their requirements are very more and more stringent. Accordingly, actually, the curve here is showing us what is actually the reactive control requirement for the wind generators during the low voltage events. You can understand that the S coordinate is actually the Ri versus Rn, and is rated current of the generator. Ri is definitely the reactive component of the generator, reactive current component of the overall generators. You can see that our S coordinate is the percentage of terminal voltage. You can see that if the terminal voltage is above 90%, and we can actually have around zero reactive current contribution by the wind generator. But slowly, when the terminal voltage is going down from 90 to only half of the rated, then accordingly, you need to contribute 0.9 reactive power. Of course, 0.9 stands for the per unit value. That means when it drops to the 50 percentage, the voltage, then you have to contribute 90% in terms of per unit for the reactive power, reactive current. Then in our new methods for LVRT, we actually take this into consideration to redesign the rotor side and the grid side control. We have come up with a so-called cascaded control scheme to enable, firstly, the grid side converter to contribute the reactive power to support the voltage. And if the voltage at the terminal bus still not recovered, then the second stage rotor side control will be activated to contribute reactive support to the grid by the generators. So overall, so we have in the second paper we have improved the LVRT for the proportional voltage control, and also we introduced the reactive control. Then they have tested results using these simple systems. And here we have comparing the traditional crowbar, our proposed method, as well as the demagnetizing methods. We found out that in terms of the terminal voltage, in terms of the power fluctuation, our method gave better response in terms of the quickness and effectiveness of smoothing out the voltage profile and power profiles of the defect systems. And so a short summary of our research work in this direction. We understand that the defect is a complex system involving the aerodynamic, mechanical, electrical subsystem, essential to ensure the system stability and facilitate further penetrations. Traditional LVRT have drawbacks and cannot support the reactive and voltage support during the fault. Our proposed method allows the defect to riding through the low voltage. There's no additional hardware. There's no additional energy dissipation. We only need to revise, modify the control strategies during the fault. And also, we can maximize the reactive power support during the fault by introducing cascading control schemes. So the future work actually, we move on to the hardware implementation and validation. Actually, nowadays we actually using the D-space. We have implemented such a scheme not for the wind, but we have implement this for the solar system in the D-space system by using the D-space. Extend to the full converter type already, and we're also working on frequency and inertia control for the wind turbines. for user defect or full converter time. Okay, that's all from my presentation. Thank you for your attention. So if you have any question, you can let me know.
Thank you, Professor, for your informative session on topics of prognosis of wind generation and wind penetrated grid and low voltage ride-through control for DFIG wind turbine system. The session is now open for discussion. Please unmute your mic and raise your query.
Isma, there is one question. You can read out.
Yeah, there is one query in chat box. How do you validate and verify an ANN model for forecasting? What is the allowable range of mean squared error and mean absolute error in ANN?
Okay, it's a very good question. It's validation of the forecasting model is always problematic, to be honest, because it's very dependent on many factors, particularly the data. So according to our experience in the AN models for forecasting, so as I said already, the models can hardly give you consistent performance for different data profiles. For example, because we know that obviously the wind and other renewables might have the we call the seasonal patterns, or they also have daily patterns. So it according to our experience that in terms of the errors, forecasting error, it always varies from season to season, and sometimes from daytime to the night. So when we do the forecasting, when we do the research for this based renewable forecasting, we have to be careful that we have to organize our validation or our verification by considering the data sets from different seasons throughout the years, and perhaps even different months throughout the years, to ensure that results is kind of universally reliable. Model is universally reliable across. This can be very difficult. That's why in a lot of see the researchers are introducing so-called ensemble models. That means multiple models to accommodate this uncertainty or across different data sets. Also, there are other methods to handle that. Regarding the allowable mean square errors and mean absolute errors, really depending on the users. For example, if you are wind farm operator, wind farm owners, I'm not sure what's the situation in India, but according to my knowledge, that talk to some of the wind power company in mainland China. Nowadays, the power system operator will request all those most those wind companies to submit their ahead forecasting profiles, and then they will get the penalty if their errors. I remember if their errors is go over 5%, they will get penalties, very heavy penalties. Therefore, this question of range of mean square error, mean absolute error, really depending on the application, the users. In the mainland China case, it's really the system operator will apply penalties. By percentage becomes very critical. So perhaps in India, there's different penalty. Yeah.
There is one more query. Thank you, sir. There is one more query in the chat box. Why are researchers using IEEE or IEC standard while designing a microgrid system? What compatibility is there? What is its significance?
EEE, IEC, of course, they are the leading organization for the standardization. So that's why the standards actually published by them are kind of well accepted by many countries. And therefore, especially not only those are different national grids, but also the manufacturers use their standards. So the reasons we're doing that is simply because in practice the manufacturers supplying the equipments from grid systems in line with those EEE IEC, particularly IEC standards. So EEE sometimes may be very sort of relevant for the US system, which is the 60 hertz system. So IEC is mostly for kind of popular or dominant in Europe and also in mainland China, and I believe in many other Asian. So by aligning with those IEC standards, of course, we can make sure all the equipments have the compatibilities. And this is to actually avoid those interfacing problems in terms of the communication protocols, data format, and etc., so that we can have troubles in solving those problems. That's the major reasons why we are adopting the international standards.